Today we're looking at using ePOP concept to evaluate and analyze different ways to deliver power. We're going to start at the application screen where the cycle is loaded. In this case, it's an electrical power delivery, 1 kilowatt average, 2 kilowatt peak over this 5-hour duration. So a simple cycle, 5 kilowatt hours total. But there are different configurations to deliver that power. So we move to the configuration screen. Here is one way, a typical ICE generator configuration. We'll go to the hybrid configuration. This is a series plug-in hybrid. And you see that there's an addition of a charger and a battery associated with it. So now this configuration has the ability to use a battery to deliver that power. Now, in addition to different configurations, you can see different configurations here. There's different technologies within that configuration that can be applied, which has an impact on the power delivery. Now, what we're wanting to do is use ePOP concept to see what the trade-offs are between the different options. So here we have the KPI of mass selected, and here's the generator configuration, which is 100% ICE, no battery, and this line that you see here is the hybrid configuration, which could be everything electrified up into and including 100% battery, no generator, no ICE generator on board, and really every increment of a hybrid in between. But you can see if mass is your KPI, there's basically a 5 times mass penalty adding the battery to meet this power profile. As you scale anywhere, the battery down, the configuration of ePOP concept changes. There's a trade-off of mass for increments of increasing battery, all to deliver the same profile. So you may ask, why would we ever use battery? The reality, we'll go back to the application, is it can get more complicated than that. What if instead of a 2 kilowatt peak, you had to deliver 10 kilowatts instantaneously on the profile? How does that change the results? And now you can see mass as the KPI. There's a clear knee in the curve. If you were just doing ICE only, actually pay a mass penalty over a hybrid ICE and battery system. And if you went again all the way to battery, it would be an increase in mass, not as much as our first example with the 2 kilowatts, but you can see now there's trade-offs that maybe aren't as clear. So the actual optimization that you would do, mass optimization that you would do for this application is different than the one we started with. There are, in addition to mass and volume, there's initial cost, total cost, and total cost of ownership depends on the cycle. In this case, it's 5 cycles per week for 8 years with the electricity or fuel, the energy defined. Now, if you go back and you want to change it, this is a series plug-in. You change it to a non-plug-in, where you can see the total cost of ownership adjusted because the economics of plugging in versus generating on board change if it's non-plug-in. So these are complicated trade-offs: cost, mass, volume. There's also It's called a power source duration. The ice generator can generate this for 10 minutes, but it can pretty much do that continuously. But if you go to an hour duration, now your battery configuration is dropped below the ice. If you go to 3 hours, it's changed further still. So what batteries can deliver in the short term is different than what they can deliver in the long term. And it gets complicated depending on what that time is. But if we go back to the application and change, instead of a 5-hour duration, let's say the requirement is a 2-hour duration, and we go back to the results. Now the solution for a 2-hour duration, the solution is more batteries than it is ice. You're able to, while increasing the batteries, you're able to downsize the ice more than you're able to increase the batteries. Therefore, the mass optimum solution for this profile, it's a very different configuration, but the hybrid in this case is lower mass than the traditional generator. If you go to the configuration, that's assuming lithium iron phosphate batteries, LFP batteries. But if we change this to a different battery technology, you can see how that affects, what the optimum is. This is mass. So the battery technology will change where the optimum is. So only 35% of a battery-only solution is actually a mass optimum in this case, mainly from downsizing the engine, volume, initial cost with the cost as I have them defined in my technology library. But if you have different battery, this is the definition of the battery. But if there's a new battery that you want to evaluate, or new engine or generator technology, converter technology, power electronics, you put in the technology that's relevant for your application, the physics of it, the cost of it. With batteries, there's SOC or power rating characteristics, and that all feeds in to the calculations that are being updated. These are complicated trade-offs that are not intuitive, and it's important to know how what you define as your cycle in the beginning really affects what the optimum concept is in the end. ePOP concept makes the trade-offs clear and intuitive.